Thank you. Right, hold your applause till afterwards, and you can judge it. Right. Sorry for the late start. Okay, so this is a talk about modern Java, in which change is the only constant. In the last couple of years, we've changed the Java platform in 3 ways that we never have before. First, we took this massive monolithic platform that had grown monotonically over time, and we sliced it up into 26 standard modules. Second, we removed the Java EE and Corba modules and some other APIs, leaving us with 19 standard modules. And third, we left behind our historically grand and majestic but rather slow-moving and unpredictable release model in which we shipped a major release every 2 to 5 or, well, in one case even 7 years. We replaced it with a rapid cadence release model in which we ship a new feature release every 6 months on a strict time-based schedule. Now, modularizing the platform and removing submodules did break a few things. Many have wondered whether the Java ecosystem will be able to keep up with a 6-month release cadence. Taken together, all of these changes are, frankly, somewhat scary, but maybe not as scary as you think. Why did we make them? Because adapt or perish now as ever is nature's inexorable imperative, according to H.G. Wells. Or if you prefer a more modern formulation, adapt or die. So saith Andy Grove. We must change Java in new ways because its competitive environment is very different than it was 20 years ago. There have been 2 big changes. First, many popular platforms ship new features around once a year, if not every 6 months. If Java is to remain competitive, we must move it forward faster. Second, applications are packaged and deployed in different ways than they were 20 years ago, whether to the cloud or in packaged apps published to app stores. If Java is to remain competitive, then we must adapt it to these new environments. Let's take a look at the first big change, modularizing the platform. This is where we ended up. Nice, clean module graph, 26 standard modules, the Java base module at the bottom, perhaps the most important one. All other modules implicitly depend upon Java Base, and Java Base is the one module that depends upon no others. The JDK has these standard modules plus many more non-standard modules that contain development and debugging tools, service providers, and some JDK-specific APIs. This beautiful graph is not where we started. Where we started was with a spaghetti bowl of tightly coupled platform components with sometimes surprising interconnections. If you trace through all the dependencies here, if you wanted to print hello world, you actually needed Corba. Okay. Slicing all this up while maintaining as much compatibility as possible took years of painstaking refactoring and delicate surgery. We were finally able to deliver on that in JDK 9. Now, modularizing an old code base can be a ton of work, but modularizing the platform yielded many benefits. One benefit is that it's more flexible. A module names the modules upon which it depends, so the compiler and the runtime system can ensure the reliable configuration of consistent subsets of the platform. Most applications, after all, don't need all of these modules. If you have an application that only uses the Java SQL and Java base modules, you can link a custom runtime system that contains just those 2 modules, plus any other modules that they need. The rest simply fall away. Now realizing that the screen is somewhat distorted. Oh well. You can package this custom runtime system with your app, leading to smaller Docker images and smaller App Store packages that are tens of megabytes rather than hundreds. To take advantage of this, you don't need to modularize your app. You can do that if you want. There are many good reasons to do so, but it can be an awful lot of work, and frankly, if your app is in maintenance mode, then it's probably not worth the trouble. Another benefit of the modular platform is that it's more secure. A module exports specific packages for use only by the modules that depend upon it, so the compiler and the runtime system can enforce strong encapsulation. How much more secure is it? Of the 6 high-impact zero-day vulnerabilities reported since JDK 7 in 2011, 3 of them would have been prevented if we'd been able to strongly encapsulate the JDK's internal APIs. A final benefit of the modular platform is that it's easier to maintain. The JDK does have many internal APIs never meant to be used by external code. For decades, we've been warning people against using these. They've done that anyway, of course, sometimes in some extremely popular libraries. Now, to be fair, in some cases, these library developers were after critical functionality that was available in no other way. So, okay, fair play, that's fine. But in many cases, you know, we can all be lazy. We're developers after all. Why write your own base64 decoder when there's a perfectly good one over in the SunMISC package? For many years, we've therefore treated most internal APIs almost as if they were standard. We've been reluctant to change them because we don't want to break people's code. But this has made the platform harder to maintain and harder to evolve. With strong encapsulation, we can close off all access to the internal APIs of the JDK simply by not exporting the packages that contain them. If we did that right away, we would definitely break a lot of existing code. So we're taking a more gradual, nuanced approach, since migration takes time, especially in such a large ecosystem. Starting with JDK 9, and at least through JDK 11, if your code uses JDK internal APIs, then it will not compile, and it may generate warnings at runtime. By your code, I mean not just the code that you write, but all those glorious libraries you downloaded from Maven Central. Don't forget about those. We have deliberately relaxed the strong encapsulation of legacy JDK internal packages for now at runtime so that old code will continue to run. We will eventually strengthen the encapsulation of these packages once we've provided standard APIs for the critical internal APIs and once everyone has had a chance to fix their old code. When we do that, in some future release, code that uses JDK internal APIs will not run. In the meantime, here's an example of the kind of warning you might see if you haven't seen one of these already. This is a log of Jython, a Python interpreter written in Java running on JDK 9. You would see the exact same thing if it were running on 11, 12, or 13. It tells you an illegal reflective access operation has occurred. It identifies the code responsible and the internal API that it accessed. It suggests that you report this error to the maintainers of the errant library so that you can do your part to help move the ecosystem forward. It tells you how to get additional warnings if you want to see them, because by default only the first such warning will be shown. And of course, there might be hundreds or even thousands, who knows. And finally, it reminds you that all illegal access operations will be denied in a future release. To help you get ready for that future, when such code will not run, we introduced a new tool in JDK 9 called JDEPS. If you run JDEPS against an existing jar file with the JDK internals option, it can detect most uses of internal APIs. As an example, here it detected the use of sun.security.x509.x500 name, very popular class. It is an internal API. It even suggested a standard replacement. And note that the @since 1.4. When did Java 1.4 ship? Anybody know?
2006.
2006? No, further. 2002, 17 years ago. There's really no excuse not to be using the standard API here. Anyway, JDEPS, recommend that you use it. The modular platform does break some things, but it doesn't break everything. In fact, if your code uses only standard Java SE APIs, then it most likely will work without change. I say most likely because there are some very minor differences. We removed a few obscure, rarely used methods and mechanisms to enable that clean modularization. We also made a few behavioral changes that honor the specification, but in rare cases might break existing code. If you want to know more, have a look at JEP 261, which lays out all the compatibility-related changes in great, gory detail. Beyond that, to learn more about Java modules and the modular platform, I can recommend all three of these excellent books. So the modular platform enabled the second big change of the past year. We've reduced the platform by actually removing things for the first time in Java's history. Well, at least the first time on purpose. We removed the Java EE and Corba modules in Java 11. Why? Well, the details are in JEP 320, but in a nutshell, these components are costly to maintain. They've been the source of multiple security vulnerabilities over the years, and nowadays they're either available elsewhere, as in the case of Java EE, which is now at Eclipse and is called Jakarta EE, or they're no longer relevant, as in the case of Corba. We removed some other smaller things too. As I mentioned, in order to modularize the platform cleanly, we removed some fairly obscure methods in Java 9. Most of these had to do with configuring property change listeners on various core APIs. These methods probably never should have been added in the first place. They were sort of an abstraction, boundary violation, putting AWT methods in core classes. Really? Okay, but there they were. We removed these only after analyzing a lot of code out in the wild to see if anyone was using them, and hardly anyone was. While we were at it, we also removed a pointless constructor that somehow accidentally snuck into Java 8. We removed more methods in Java 10. All of these methods are ill-defined, actively harmful, don't work, or don't do anything useful. We removed yet more such methods and one class in Java 11. Removing things can cause breakage. To ease the pain, we always give advance notice by deprecating APIs to be removed at least one release in advance, and often more. As an example of that advance notice, here are all the APIs deprecated in Java 11 for removal in a future release. If you look closely, you'll see that this list mentions many finalize methods in the core APIs, which we're removing because finalization is a fundamentally broken mechanism that we've replaced with something better. When an API is deprecated for removal, that's always noted in the API's Java doc. For example, here's a method. This is a very old method, goes all the way back to Java pre-1.0, back when we only had bytecode interpreters. We didn't have JITs that compiled. This is about tracing method calls. You read the deprecation notice, intended to control method call tracing has been superseded by JVM-specific tracing mechanisms. Note the subtle and sophisticated specification not implemented does nothing. Nobody's going to miss this. If you compile source code that uses an API that's deprecated for removal, then the compiler will helpfully warn you about it. All right, popping up. First, we modularized the platform, and then we trimmed it down, and then we started moving it forward at a faster pace with a new release every 6 months. How can that possibly work? Let's look at the timeline. We shipped JDK 9 in September 2017. We shipped 10 just over a year ago in March 2018. We shipped 11 last September and 12 just 6 weeks ago, this past March. We'll ship JDK 13 in September of this year, and so on every 6 months, like clockwork. Now, one of these feature releases can contain any kind of feature, a language feature, a VM feature, a performance feature, a library feature. It can even remove an old feature. For this to work, features can only go in when they're nearly finished, because we can no longer slip a release in order to fix a broken feature, something that we did all too often in the past, frankly. But that's okay, because if a feature misses the current release, the next one is just 6 months away. It's no big deal. At the beginning of all this was JDK 9, the final massive JDK release. There were 90 JEPs in JDK 9. We shipped it 3 years and 6 months after JDK 8, which had shipped in 2014. There were 2 major slips to the schedule, and both of them were my fault. Oracle engineers did much of this work, but not all of it. 6 JEPs came from outside Oracle by contributors from Red Hat, Linaro, and SAP, plus 2 independents, Doug Lee and Laurent Borges. These non-Oracle contributions were significant. They included 3 CPU ports, some important performance work, and a brand new 2D graphics rasterizer. So after all this, what was going to be in JDK 10? One worry we actually had about the 6-month cadence was there might be 0 features in a release. It's theoretically possible after all. If you're going to ship like clockwork, then every 6 months you ship what you've got, and maybe we could ship a release that just has some bug fixes and small enhancements in it rather than any bigger features. Happily, that turned out not to be the case. JDK 10 contained 12 JEPs, including 1 language feature, local variable type inference, some more performance work, a massive refactoring of the source code into a single Mercurial repository. Again, Oracle engineers did much of this work, but 2 JEPs came from other contributors. JEP 304 was a GC interface built by Roman Kenki at Red Hat. And JEP 316 from some engineers at Intel. They implemented heap allocation on alternative memory devices. This pattern continued with JDK 11, which contains 17 JEPs, including some long-needed JVM improvements, a new HTTP client API, The ability to launch single-file source code programs, which many people laugh at first, but it turns out to be really, really useful. And also TLS 1.3, just in time for the final Internet standard. Oracle engineers did, again, do most of this work, but 3GEPs were contributed by others. From Belsoft and Cavium, we got some ARM64 performance improvements. Alexei Shiplev at Red Hat contributed the Epsilon garbage collector, which isn't really a garbage collector because it never collects anything, but that's sometimes useful for benchmarks. And John-Christoph Weiler at Google contributed low overhead heap profiling. Moving on to JDK 12, there were 8 JEPs, including a micro benchmark suite for the JDK itself, a preview language feature, switch expressions, and various VM performance improvements. Oracle, yes, did most of this work, but in JDK 12, we do have an entire new garbage collector, Shenandoah, contributed by engineers at Red Hat. As you can see, I hope, what has changed here is not the rate of innovation, but the rate of innovation delivery. In 3 years, by 2021 or so, we probably will have merged around 90 JEPs, just as we had in JDK 9. Now, these feature releases aren't just about JEPs, of course. Each contains many smaller enhancements and bug fixes. As an example, according to our bug database, we resolved almost 2,500 issues in JDK 11. Oracle engineers worked on most of these, but there were significant contributions from others, including engineers at SAP, Red Hat, Google, a bunch of individuals, and Belsoft. Returning to our timeline then. The 6-month cadence will enable Java better to compete with other platforms. But you might be wondering, what about updates, security fixes, critical patches? The plan in the OpenJDK community is to update the current feature release for at least 6 months. That's 2 quarterly update releases. And then every 3 years, we'll declare a long-term support release. The first being 11, which shipped last September. The next being 17 in 2021. If you like, you can think of JDK 8 sitting way up there, being the previous long-term support release. Each of these long-term support releases will be updated well past the beginning of the next LTS release, and possibly even longer. You might think that the non-LTS releases are in some way experimental. Oh, they're just a fancy name for a beta, I've heard some people say. But they're not. Every release is production ready. What differs is only the length of the support timeline. So, you have a new kind of choice to make. You can take the blue pill or the red pill. You take the blue pill, you wake up in your bed and continue to develop and deploy uncomfortable, conservatively managed, slow-moving LTS releases with an update release every quarter and a major migration every 3 years. You take the red pill and you go down the rabbit hole, where you can enjoy the latest language features, API enhancements, performance improvements, and bug fixes with a minor migration every 6 months. It's up to you. All I offer is the truth. If you do choose the LTS path and take the blue pill, you might be wondering, who will produce your update releases? Again, you have a choice to make. Since JDK 9, Oracle contributors in the OpenJDK community have focused and will continue to focus primarily on feature releases rather than on updates. Oracle will ship OpenJDK builds under the GPL for the first 6 months of each feature release. That's the GA plus 2 updates, whether that release is a long-term support release or not. After that, Oracle will offer long-term support builds, but in a change from the past, these will be available only under a commercial license that allows free use for development and testing, but requires payment for use in production. That might sound scary, but don't worry. Java is still free. All of the code is still available under the GPL for anyone to build, test, publish, update, and support. Oracle engineers won't regularly contribute to, much less lead, the LTS releases as they have in the past. But that's okay. The OpenJDK community as a whole has a proven track record of transitioning the leadership of update releases from Oracle engineers to non-Oracle engineers. We did that years ago for JDK 6 and JDK 7. We did it again for JDK 8 and JDK 11 earlier this year when Andrew Haley, Red Hat's Java platform lead, took on the leadership of the JDK 8 and JDK 11 updates projects. And this isn't just my personal fantasy. As Andrew has assured everyone, Whether by Oracle or Red Hat or someone else, JDK LTS releases will continue to be supported. We all have a lot invested in Java, and we won't let it fall. The LTS work will carry on in the OpenJDK community as it has in the past. You'll be able to get carefully built, well-tested JDK LTS builds based upon that source code in any Linux distribution, whether derived from Red Hat, Debian, Gentoo, or Arch. If you're not on Linux, you'll be able to get LTS builds for free from a variety of providers. For this plan to work, it's critical that you be able to switch from one provider to another. In past release, this wasn't quite possible since Oracle always held back a few so-called commercial features that were only available to paying customers. These included application class data sharing, Java Flight Recorder, Java Mission Control, and the Z garbage collector. To enable such switching and to establish a level playing field for all, over the past 2 years, Oracle open-sourced these commercial features so that Oracle builds and OpenJDK builds are functionally interchangeable. You can switch from one provider to another as you please. When you choose a provider, though, you might want to consider those with the depth of knowledge that comes only from a long-term commitment to the platform. You have a choice. You take the blue pill or the red pill. You can choose the conservative LTS path and take the blue pill with a major migration every 3 years. That can be a good choice for a conventional enterprise-style deployment of large applications on large servers. Or you can choose the fast-moving feature release path and take the red pill with a small migration every 6 months. That can be a good choice if you're deploying to the cloud or to app stores and you're bundling the JRE or the subset of Java that you need with your app. If you choose the LTS path and take the blue pill, then you shouldn't ignore the non-LTS releases. Some free advice. If you maintain an infrequently migrated system, then you should still test it with each non-LTS release. That way you'll be nearly ready for the next LTS release by the time it's available. You're essentially spreading your migration effort out over time. If, on the other hand, you choose the adventurous feature release path and take the red pill, then you're going to migrate to each feature release as it becomes available. So make sure that your tools and dependencies can keep up. Many will be able to keep up, but some won't, especially if they're unmaintained, so plan with care. To sum up, we are evolving the Java platform at a more rapid pace in order to keep up with competing platforms. We have broken a few things and will continue to do so in order to make Java a better fit for modern applications. Are these changes really all that scary? I don't think they are, for 4 reasons. First, we'll always give advance notice before removing anything, and we'll only do so when there's a very good reason, because we don't want to break existing code unnecessarily. Compatibility remains one of the core values of the Java platform. Second, you have a choice to make, which you didn't have before. You can take the blue pill and migrate every 3 years at a comfortable stately pace, or you can take the red pill and enjoy the latest features and fixes every 6 months. Third, it's true that Oracle will no longer provide free update releases, but Java is still free. Free updates will be available from a variety of other providers, including all of the major Linux distributions. If you want active support, then you're probably going to have to pay someone or do it yourself, but that's always been the case. So choose your provider wisely. Finally, we did break a few things. Migrating past Java 8 may require some work, but it might not be as hard as you think. All 3 of the major IDEs already support all of the new language features, even the ones in 12. Many popular tools, libraries, and frameworks already support JDK 9, if not 11 or even 12. You don't have to take my word on this. Just after Java 9 was released, some of you might recall this, I asked on Twitter, do you maintain a popular Java library, framework, or tool? If it works fine on JDK 9, then please reply with its name and version. That was way back in 2017, ancient history at this point. So shortly after JDK 11 was released last fall, I asked, do you maintain a popular Java library, framework, or tool? If it works like heaven on JDK 11, then please reply with its name and version. My thanks to Sam Brannon of the JUnit team for the hashtag. I saw many, many responses. All 93 of these libraries, frameworks, and tools work just fine on JDK 9. They worked without change, or their maintainers fixed them, and in many cases, it wasn't that hard. These include the build tools, Ant, Maven, and Gradle, test frameworks, JUnit, TestNG, popular libraries, ByteBuddy, Jackson, Log4j, Hibernate, Juke, Netty. The entire Spring framework is here. 51 of these components work not just fine on JDK 9, but like heaven on 11. Since the transition from 9 to 11 is much easier than the transition from 8 to 9, I expect that the rest of them will catch up in short order. Maybe they already have. My most urgent advice to you today, then, is this. If you're using Java 9 or later, upgrade to the latest versions of all your tools and dependencies, because everything changes and nothing stands still. So, at this point, I was going to show some demos of features that we've shipped recently, of features that are in the pipeline. It's actually a really exciting time in Java right now because our feature pipeline is the richest and fullest that it's been in years. We've got some really exciting stuff in the works with Project Loom and Fibers, Valhalla, and value types. Unfortunately, here at CERN, with all of the wonderful technology, it is unable to talk to the machine upon which I do the demos. One more thing I must do to satisfy my employment contract. Don't believe a word I've said. Thank you very much.